Hello again and welcome to another review session for your final exam in Calculus 3208 presented by CDLI. And in this session today we're looking at a couple of extension items that relate to implicit differentiation, so some applications thereof. So let's look at what those topics are. The first thing we want to do with this is we want to find the equation of a normal or tangent line to any implicit curve at a particular point. And we also want to be able to find the second derivative of an implicit relation using our techniques that we know for implicit differentiation. So lots of fun things to tackle there. Let's get started. So first of all, I've got an example worked out here for finding the tangent and normal line to an implicit curve. So if you look over here on the left, or sorry, on the right, if I can direct your attention over here on the right, you see you've got this cagey looking sort of blue curve. And I've drawn a tangent line and a normal line at the point 1, 2. So I don't want to go through all the details of the algebra and such with this. I just want to give you an idea, like an overview of how this works, what we would have to do here, and then we'll get the rest of it worked out when we get into some examples shortly. So the first thing we do is consider the implicit curve that's given by that equation. And I'm going to apply my techniques of implicit differentiation. So my first term, 2x cubed becomes 6x squared. And then I've got to use a product rule with xy there, so I'm subtracting that. End up with y plus x dy over dx. And then 2y becomes, or sorry, y squared up here becomes 2y times dy over dx. And the derivative of 4 is, of course, 0. So a little bit of algebra from all of that, and we end up with our first derivative, dy over dx equals y minus 6x squared over 2y minus x. So if you can, you try to isolate dy over dx to get your implicit derivative. So then if I want to find the equation of my tangent and the equation of my normal, all I have to do is evaluate that derivative at the point in question. So we're used to finding equations of tangent lines, and all we need to find the slope is just the value of x to plug it into our f prime of x, we'll say. But in this case, because we have an implicit function, we can actually find the value of our derivative by plugging in values for both x and y to our derivative. And when we do that here, we find the slope of the tangent has to be minus 4/3. So we want an equation of a line that has that slope and passes through the point 1, 2. So writing that quickly in slope point form would look just like this. And of course, for the equation of the normal line in slope point form, it'll look almost identical to that, except I change my negative 4/3 for a perpendicular line, and I have a slope of 3/4. Okay? So there we go, switching from tangent to normal line by just changing the slope, and everything else will look the same when we're in slope point form. All right, the other thing we wanted to look at is how do we find the second derivative for an implicit relation. So to find the second derivative of an implicit relation, what we do is we start with our curve, which is right here. And then we can find the first derivative, of course, using our implicit differentiation techniques. So the first thing we do over here is find dy over dx. So for this particular function, or sorry, relation, 2x cubed becomes 6x squared, and 3y squared becomes 6y, multiplied by the derivative of the function y, and we have dy over dx. And then, of course, negative 6 has a derivative of 0. So a quick algebraic rearrangement there gives us dy over dx is x squared over y with a negative out in front. Alrighty, so the next thing we have to do, if we want to find the second derivative, is just go ahead and differentiate again and see what happens. So we find the second derivative here, so this is going to require a quotient rule, which was what was done in this case. So there's a quotient rule, except remember when we differentiate the denominator in the second term of our quotient rule on the numerator here, we have this dy over dx sticking around. So what this actually creates is something called a differential equation, because we have a derivative inside the context of our equation for our second derivative. And that's a bit messy, so we don't like to have that. So what we want to do then is find a way to get rid of that derivative, and it just turns out that we already know an expression for dy over dx from the previous work. So we just take that and we plug it in where dy over dx is in our second derivative, and it just fits in right here nicely. So then all we have to do is some more algebra to simplify this. So when we start simplifying, we get positive x squared over y for that term, getting a common denominator in my numerator of y there. and leaving this stuff up top, multiplying by the reciprocal of the denominator, and we have our simplified version. So don't worry about the algebraic details on that too much. As I said, we're going to do some examples shortly. But the basic idea is start with your implicit curve, or your relation that we have. And for that, we find our first derivative using implicit differentiation. Then we find our second derivative by just reiterating that process. And then, because we have this extra dy over dx here, or however many of those we might have, we replace it with what we knew dy over dx was to give us this, and then it's a matter of simplifying with some algebra. Okay, let's get rolling. So our first example says, use implicit differentiation to find the equation of the tangent line to the given curve at the point 0 and 1/2. So the first thing we're going to want to do here is find our implicit derivative. So we'll start by saying that'll be 2x plus y squared will be 2y multiplied by dy over dx, like so. And on the other side, I've got to attack this with a chain rule, so it's 2 outside of 2x squared plus 2y squared minus x. Leave all the inside stuff alone at first, and then multiply by its derivative. So I'm multiplying by 4x plus 4y times dy over dx, and then subtract 1 for the derivative of x. And so there I have taken my implicit derivative. So x should look a little more like an x, I suppose. So what I have to do now is I could try to rearrange all of this to get dy over dx by itself. But because of this right here, and when we ended up with our derivative, we now have a big ugly trinomial here multiplied by another big ugly trinomial here, and that's equal to a binomial over on this side. That's a little bit hairy. So what we're going to do is we're going to cheat just ever so slightly, because the question doesn't say isolate dy over dx. The question says find the equation of the tangent. So all we need to know is the value of dy over dx when x equals 0 and y equals 1/2. So all I'm going to do here is I'm just going to fill those values into x and y at this stage and see where it takes us. So my first side of the equation over on the left, I'm going to get that when I fill in my numbers for x and y. And then on the right side of the equation, I'll have 2 times 0 squared plus 2 times 1/2 squared there minus 0. And all that gets multiplied by 4 by 0 plus 4 times 1/2, which sounds like a nice number, times dy over dx, and then subtract 1. So we have all that. And so now we'll start simplifying. 2 zeros are 0, 2 zeros squared are still 0, 0 is 0, and 4 zeros are 0. So all of a sudden this is going to get really neat really fast. So 2 times 1/2 becomes 1, so my left side is just dy by dx, and that's nice. And then on the right side, inside these brackets, I have 2 times 1/2 squared, so that's going to be 2 times 1/4, which is 1/2, multiplied by another 2, which is just 1. So all this stuff out here is just equal to 1. So 1 multiplied by this stuff over here isn't going to make much of a difference. So I'm just going to have 4 times 1/2, which is 2, dy over dx, and then subtract 1 times 1, which is a 1 there. Okay, so quickly solving now for dy over dx, I'll subtract it from both sides, so I just get 1 dy by dx on the right, and adding 1 to the other side, we have our derivative is equal to 1. Okay, so I'm just going to make a quick note of that over here. Dy over dx, the slope of the tangent, turned out to be 1, so then I can get rid of all the other junk. So if you're taking a minute to write all that down, if that's the kind of thing you're doing there as you study, then maybe pause the video for a second. Do that, otherwise I'm just going to delete it to get it out of our hair. The important thing is now we know that the value of the derivative is 1 at that point. So if I'm going to write the equation of the tangent line, I know that my tangent line will be y equals my slope times x minus the x coordinate of the point we know plus the y coordinate of the point that we know, and it looks like this. So that's simply 1x plus 1/2. And there is the equation of our tangent line. So that looked a little bit ominous for a second there, but using some quick thinking we were able to get through that. Okay, next example. We have to say, given this implicit relation, show that the second derivative is equal to that stuff over there. Okay. Good thing and bad thing about this question. The bad thing about it is it means we're going to have to do a lot of simplifying, likely to get to the point that they want there for this question. But the good thing about it is, at least if we get there, we know we've got it right. So let's give it a whirl. So we'll start with finding our first derivative to start off with. So we've got a product rule for these two guys. So that's going to give us 1 times y plus dy over dx times x, plus, for this business, I'm going to have 2y by dy over dx, and the derivative of 1 is 0. Okie doke. So I'll collect my dy over dx terms on the left side of this equation, and I've got dy over dx times x plus 2y, when I factor it out, is going to be equal to minus y. So I end up with dy over dx here is equal to negative y divided by x and 2y in my denominator. Okay, so what I'm going to do is, instead of leaving all that stuff there, we've got a fair bit of algebra left to do in this problem yet. So I'm just going to take that and I'm going to make a little note up here at the top for myself to say, I've already found my first derivative, and this is what it was. So it's negative y over x plus 2y. All right, so let's get rid of all the space junk and see if we can find our way back to Earth here. So there goes the space junk. Now, our next step is going to be, we've got to take our expression that we now have for dy over dx and differentiate it again and see if we get anything that remotely resembles that. We probably won't at first, but we'll get there eventually. So d squared y over dx squared, in this case, is going to be equal to, for dy over dx, we have a quotient rule. So the derivative of the top, well, before I even do that, on this function, I'm going to write it as negative y outside of x plus 2y, just to make it a little easier to differentiate. So I'm just going to carry the negative out in front instead of having to use it as part of one of my terms. So the derivative of the numerator now will be dy over dx multiplied by the denominator, which will be x plus 2y. And then I subtract the derivative of that denominator. So the derivative of that denominator is going to be 1 plus 2 times dy over dx, all multiplied by the numerator, which is just a positive y now since I put that negative out in front. And then the denominator of this monster will be x plus 2y, all squared. Okay, so that looks like a lovely monster. So what I'm going to do now is at least try to simplify a few things here before I plug my dy over dx expression into this to make it a little nicer. So, using distributive property on this part of my expression, I've got x times dy over dx plus 2y times dy over dx, and then I have to multiply both of these terms by y and change their signs. So this will be negative y and then minus 2y by dy over dx. And I think I see the first thing that's going to come out of this that's a little bit nice anyway so far. So we have x plus 2y squared in the denominator, and that thing I was referring to is that if we look carefully here, this term and this term are almost the same thing, but they're negatives, so they add up to 0, and we can throw them in the trash. So what we're left with then becomes a negative outside of dy over dx right here, and then minus just a y right there, all over x plus 2y squared. Okay, so the next thing for us then is going to be to change the dy over dx into what we know our first derivative was equal to, which is this stuff up here. Okay, so we've got a negative now, and our fraction becomes negative y over x plus 2y, and then subtract a y. Now I know to get those two together, I'm eventually going to need to use a common denominator here, so I just as well to get myself going on that early. So x plus 2y and x plus 2y, and that'll get me a common denominator for that business. And this is all over x plus 2y all squared. Alrighty, So when we sort of make the algebra happen with that part, we've got a negative outside of. So I've got a common denominator, and my numerators for all of that will be negative y, and I'm going to have minus x times y, and then minus 2y squared, all over x plus 2y squared. Sorry, x plus 2y just for this part. The x plus 2y squared is down here, isn't it? Yeah, alrighty. Okay, so now I'm going to think that this will become the reciprocal of my denominator multiplied by my numerator. Yikes. Okay, so this will be, my numerator will remain for the moment as negative y minus xy minus 2y squared all over x plus 2y. And then I'm going to say multiplied by 1 over x plus 2y squared. Okie dokie. Does that look like I've got stuff done almost right there? Anyway, let's have a second look through it all. Okay. Oh, looks like I missed something way back here. I had x times dy over dx, not just dy over dx. Oops, so there should be an x in front of that, which means that there should be an x there. So that negative y should actually be negative xy all the way through there. So that's going to be negative xy all the way through there. Very sorry for that, but it'll only take a second to fix it up, I think. So that should be a negative xy all the way through. Okay, so what that gives me then is the negative out in front of. My denominator will be x plus 2y now cubed, and in my numerator I've got negative 2xy's minus 2y squared. And from that now, I still have this negative, and I'm looking at what I'm supposed to get for my answer. And I see the denominator's intact, and somehow that entire numerator has to be equal to 2. Well, some things I can do there. I can try a common factor of negative 2y, which would be the greatest common factor. But if I just want to have a 2 left over, maybe I'll try a common factor of just negative 2 and see what that does for us. So that'll give us xy minus y squared. If I take it just the minus 2, and that's all over x plus 2y cubed. Aha! So we can say subtracting a negative is adding a positive, so that goes away. And if I could get rid of all of this stuff right here, I'd be a happy guy because I'd have what I want. And if I look all the way back at my original relation, oh my goodness, look at that. xy plus y squared is equal to 1, and I factored out that negative, and that's exactly what I have there, is xy plus y squared. So that's all just 1, so this leaves me with just 2 over x plus 2y all cubed. And boy, was that a fun one. Okie doke. Let's move on to the next stuff. We got there, but I'm glad it's over. All right, next one. Here we go. It's the your turn question. It says find the equation of the normal line to that curve at the point 10, 9. So x equals 10, y equals 9. Take a few minutes and work through that. And the solution I'm going to look at now. So there's the solution worked out in its details that you need to know. And then we'll highlight some of the key features of what we did in this session. So our key features include what we can use implicit differentiation for, and we can use it to find, first of all, the second derivative of an implicit relation. So this is the 3-step process that we're highlighting here. Find and isolate y prime, then differentiate again to get y double prime, but you'll have it in terms of x, y, and y prime. So then you go back and replace the y prime you had with the expression in the first step, and then simplify. Okay, so we also can find the equation of a normal or a tangent line to an implicit curve by using implicit differentiation to find the slope at the point of tangency. And Using both coordinates at the point of tangency, A and B, we can find the value of that slope and use it to find the equation of the required line. Lots of fun stuff there. Extension things with implicit differentiation. I enjoyed it. Hope your studying is going very well. All the best of luck on your exams.